So as I was saying, right, do not scroll down, do not read and so on. So now you tell me what is stress, right? All of you know that. What is the stress? Most of you are saying, you see, when I ask you a question, you just pause my video and think and come up with an answer and try to be very accurate in your mind, and later on you can compare. So most of you are saying that stress is force upon area, force divided by area. Okay, this is right. Okay, let me ask you now, what is pressure? What is pressure? You are again saying it is force upon area, right? Agree? So according to your definition, pressure and stress are the same. Yes or no? According to your definition, they are. In reality, is pressure and stress, are they the same terms? Now some of you are saying that, you see, pressure is for liquids and so on. Stress is for solids. Do all of you agree? I don't know if you do, but no. Yes, we talk of pressure when we are talking of gases and liquids, but it does not mean that pressure is not there on solids, right? If there is a wall and you push against the wall, you are pressurizing the wall. During the course, the teacher is giving you tough exams. The teacher is pressurizing you, okay? But no, pressure and stress, it is not necessary that pressure is only for liquids and gases and stress is there for solids. Both are there for solids and liquids and gases. So what is the difference between pressure and stress? Anybody? What is the difference between pressure and stress? If mathematically stress is also force divided by area and pressure is also force divided by area, then what is the difference? Pause my lecture and think on it. Maybe some of you have a very clear idea based on your solid mechanics course. Maybe some of you did not pay a lot of attention at that time. It is just the direction of the load. You see, there is a material. There is a small, say, flat block of material. It is metal, or for example, your table, the table on which you work and so on, right? When you apply force on the table, you are applying a force from the outside. You are applying force from the outside. So this outside applied force per unit area divided by the area on which you apply, this is pressure, right? When you say that this is force divided by area, but which force? The force which is being applied from the outside. Now what is the material feeling? You see, you are applying a pressure on the material. What is the feeling of the material? Just think that it is not the table, it is your body, your body. Your friend, you ask your friend, you stand against the wall and you ask your friend to press your body. With a little force, you don't feel too much, but when he increases the force a lot, then you start feeling pain and so on. So the material of your body is feeling, it is reacting. If now you ask your friend to hit you with a box, right, like a boxer, hopefully that is not done, but you feel much more pain, right? So this is this feeling or this reaction of the material from the inside. So now back to the table. When you apply a force or a load on the table, then this applied force divided by the original area is the pressure. But if you try to find out the reaction of the material to this force, the internal reaction of the material to this applied force, then it is called a stress. The material is stressed. You are applying pressure and the material is feeling stressed. Just like in a course, right? I am trying to teach you, so I am putting a force on you, pressure, and you are stressed or not depends on your strength, isn't it? So the only difference between pressure and stress is that, are you talking from the outside applied side or are you talking from the inside material reaction? So this is it. So now if you see, a stress is the internal material response to externally applied force on a per unit area basis, right? So this is a beautiful definition. The external applied force per unit area is pressure. The internal material response per unit area is a stress. So hopefully you already had this very clear idea, but I wanted to further enforce it. Now go back to the heading. It does not say a stress and a strain. It says engineering stress and strain. So what does it mean? I mean, if we go to the College of Science, then will the scientific stress and strain be different? Engineering stress and strain is different. Is the word engineering here? Because in engineering, we define stress and strain differently. In the College of Science, we define physics and so on. No. We will see later on, you already know that there are two types of stresses and strains that we will generally discuss. The other type will be called true stress. True stress. So this one, they had to give it some name. So the name untrue will be very bad, right? It is, so just to differentiate it from the second type of stress called true stress, we call it engineering stress, right? So it is still force divided by area, but when we say engineering stress, first of all, we use the symbol sigma. I have told you when we were talking of iron, why is the symbol Fe? Not because iron would be IR or I. So why was the answer? Because the original Roman name, Latin name was ferrum. So here sigma is the same as S in normal engineering. So stress S, but taking the symbol sigma. Okay. So now it is the force upon the area, but area with this 0 here, A naught. So first, the force is the average uniaxial tensile force. You are applying force only in one direction, and it is a tensile force or a compressive force, it does not matter, tensile force or a compressive force, but you are applying the force only in one direction. And why do we use the word average? You see, if you try to pull something, you cannot pull it from one single point, you have to hold some portion of the material. So there will be lots and lots of small arrows of force actually, but whatever portion you actually held, you take the average force on that whole area. So it is important that you don't say force applied, you say average force applied, because you cannot really hold any material at a single point and then pull it. You cannot, right? So therefore it is average. And the area is the original cross-sectional area. First of all, what is cross-sectional area? You have done a full course on engineering drawing, right? So you know that you have front view, side view, and you have sectional view. So sectional means sectional, that you have cut the material. If it was a rod, you have cut it into two pieces. If it was a bar rectangular, you have cut it into two pieces. So you have sectioned it. But when we say cross-sectional, what does it mean? That we have cut it exactly at 90 degrees to its length, not at an angle. You can cut it, right? It is a rod, you can cut it at a slanted angle. But when you cut it exactly perpendicular to the length direction, then it is called cross section. Not just a section, cross section, right? So if it is a smooth round bar, a cylinder, you cut it near the top, a little below it, a little below it, a little below it, in the middle, every time you will get the same area, isn't it? So that is why we call it cross-sectional area, because it is the area at the top, it is the area at the bottom, it is any area in the middle, if you cut it in such a way that the sectioning that you are doing is exactly at 90 degrees to the length. So therefore, it is the cross-sectional area. But the critical one word, which is most important in this definition, is this word original. This is the word why we call it engineering stress and not true stress. If we remove this word, If we say force upon area, then it will become the true stress. But when we say force upon original area, why are we saying it? You understand that if it was a rod, cylindrical, and you kept on pulling it until it started to deform, then because you are applying a tensile load, you are pulling it. So what will happen to the length? The length will increase. What will happen to the dia? The dia will decrease, right? So the length will keep on increasing, but the diameter or the area will keep on decreasing. But in the definition, the force is the force at any time. Right now, there is some force divided by the original area. After some time, the force is larger. After some time, the force is much larger. The force is increasing. So the force is the current force, but the area by which you divide this is the original area, not the currently changing area. If you do this, then you say this is engineering stress. And of course, it is an engineering property, a physical property, and so on. So there will be units. This is force, this is area. So in the inch-pound system, which is used in the United States, force is in pound force and area is in a square inch. So PSI, pounds per square inch. In SI system, the force is in newtons, the area is in meter square. So it is Newton per meter square. This is called a Pascal, based on the scientist named Pascal. And conversion, you of course know, kilo, mega, and so on, 10 raised to 3, 10 raised to 6, giga will be 10 raised to 9, right? Why do we do these two? Why am I talking of pounds per square inch and Newton per square meter both? Why do not we work only in this? What would you like to do during the course? Would you like me to give you problems in both systems of units or only in SI units? I'm almost sure that the whole class says SI units, please. But I am sorry, I will disappoint you. You see, this is my course. You can make requests, but you cannot make decisions. No, that is not the thing, that this is my course. We, the whole department, decides. Why do we teach in both units? You see, when you go to the real engineering world, you will have engineering relationships, import, export, design, manufacturing, with Europe and with the US both. You cannot decide wherever you go that we will do engineering business only with Europe or only with America. So as soon as you start importing and discussing and so on with the Americans, everything is an inch-pound system. So whatever they say, if you don't understand, then you will be in a big trouble, right? So therefore, whether you like it or not, it is first of all a very small thing. Conversion of units is a very small thing. You already know it from earlier classes. But whether you like it or not, the reality of the world is that the full SI system is also very functional and the full inch-pound system is also very functional. So therefore, you will have drawings and this and discussions and so on in both units. Therefore, I will try to do it in both units for you. So here we are just summarizing that you see in terms of a graphical shape or a schematic diagram, if you take a rectangular or square piece, Ft is the tensile force, right? And of course, we can pull it from both the sides, or even if it is fixed on the other side, the reaction will still be there. And the area at the top or area at the bottom or cross-sectional area anywhere in the middle, it means the same thing. So this force divided by this cross-sectional area is the engineering stress. We can do the same thing on a round bar, right? So the area A0 is here or here and the force applied is F. So whether we do it on a rectangular piece or a square piece or a rectangular piece, the definition that this is the force divided by the original cross-sectional area, not the cross-sectional area which has decreased after the application of the tensile load.